stream. Today is day number 2 of our daily programming challenge series, where we're going to be doing something daily related to programming. Today I want to do something a little different. I want to design a small little game. Games are sometimes fun, as they give us something to do on the side with programming that involves different things. What game specifically? I actually want to build something related to Tetris today. So I'm going to show you how I get started with something like this. I'm actually going to build this project mostly through just raw code, and then at the end we'll try and incorporate a graphical interface. But the graphical interface can come last because you need to focus on the actual functionality first. So we're going to try and do this within an hour if we can. Now, the first thing we're going to do is we're going to have to design a system to handle the grid for this thing. I'm going to rename this, or put this in a package, I should say. Sig.game is good. Your package can really be any name, but we want to keep all of our classes in one package if we can, so that they can all reference each other easily. So a Tetris grid, right, has a certain number of squares and a certain number of columns. I don't actually know exactly how many they are, so let's research that real quick. There we go. Is this the official, like, size of the grid? The standard Tetris board is 10 wide and 20 high. Okay, easy enough. So we're going to represent our grid using an array of rows and columns. So generally when we have a row, we're going to call them, we're just going to make an array of blocks, right? So when you're doing this, we probably want a 2-dimensional array, one to reference everything along like the x-axis, and then one along everything on the y-axis. So, and we know what the sizes are supposed to be, 10 by 24, right? Now you can see I initialized like a, what would you call it? A new class, the block itself. The block can contain really like any data we want in it. But in this case, for now we're just going to store whether or not it is active or not. By default, the block doesn't have anything in it, right? So it's considered not active. But later on, what we want to do is we want to add in like what color it is. So we can have a color value, which can be an enum. And by default, we can make it like, I don't know, blue or something. So the color class already exists, but we're actually gonna override that with a custom enum called color. I think I'm gonna have to specify enum here, not the other way around. And we will move it to its own file, because it needs to be. Alright, inside of color, we can specify different colors that we want. So we can do blue, red, green, purple, yellow. Are those all the tetraminos, whatever you want to call them? We'll say one orange. I think that's all of them, right? Something like that. Well, we'll get around to figuring them out later. But anyways, this is going to reference the wrong color, so we're actually going to choose a different representation of what color we want. We want to use... So specifying it here, import color, right? Actually, color should be in here already, so we don't have to even specify that. go. So this is now referencing our class's color value instead of a color that's created by Java. So now we have a grid. We have to initialize the grid with blocks. So we're going to do that. We already know the grid size, so we're going to actually specify that real quick. I think it's 10 by 20. Right? We might not be able to specify it this way because we might have to specify a set of 10 blocks for every, what do you call it? Array initialization is a little tricky because you need to initialize like a set amount for something. Okay, that's what we want. So initialize array elements on the right side, not the left-hand side. And so this will give us a grid of blocks. We need to actually populate the grid of blocks, so that will be in our initialization of the grid. So we'll create a constructor, and the constructor is called when it's initialized. So we'll do for int I is, now we can make these final grid width. It'll just make it easier for us to reference these. These are integers, of course. And we're gonna use 20 for the grid height here. Grid height. Something like that, right? And now we can actually use those values when we're looking for how large the grid actually is. So for each element in grid width and for each element in grid height, we are going to create a new block. Now, we don't have any constructor for the block yet, so we're going to actually create a constructor real quick to initialize these values. The block has two members that need to be set, whether or not it's active, and what color it's going to be. We'll initialize those into the local members that this object presents. So today is a lot of object-oriented management, since that's the case. We're going to initialize every block as being empty by default, and we're going to actually add one more color here, a black color, which is going to represent nothing. And so with that all set up, we now have an array of blocks. So we can actually see for ourselves that this is active by outputting the array. So doing arrays.toString on grid will output all the block pointers, assuming we initialize the grid. So now we're going to make a game class. The game class is going to contain our entry point for our application, which means it's going to have our main function in here. And when the game is started, we're just going to simply initialize a new grid. Game grid. Like so. And when we do that, we have a system.out print line here. So it's just gonna output that grid for us. So you can see here, we just get a gigantic, not gigantic list of blocks. These are actually block arrays, as far as I can tell. Yeah, because we have an array of blocks. So this is actually representing a set of blocks. You can see there's like two brackets here. And this represents one row. I don't see why it doesn't represent more rows though. So we're gonna go for deep toString here. The difference between deep toString and toString is that deep toString actually iterates through all the objects inside of every array. So here we can see a better picture. This is one array element. Here's another array element, and each one of these points to a different block in memory. So now we know each row contains these blocks. Actually, each column, excuse me. Each one of these array elements represents one column. Each column has 20 elements in it. 3, 6, 9, 12, 15, 18, 19, 20. So that is our 200 blocks ready to be used. So now we have to implement logic for the game, and we can do this in a couple of ways. But basically, in any game, you need like a step function, something where you can run every single frame, right? And it calculates like game logic. So we're going to be making a new method called step. And in the step function, we are going to run all of the game logic essentially. And so this will be called frequently by Java, like repeatedly. And we'll get to the repeatedly part later. But basically, the game logic will incorporate everything we need to do. So, in order for this, I'm actually going to move the step object into, let me see. It makes sense to put it in the game class. I don't see any other place where this would make sense, honestly. So I think putting it in here is the best idea. So that later we can call step, and we'll be calling step many times. We can do that using what's called a timer task. So if we make a task, I believe it's something like this, then we have to specify like an actual new task class, which I think can be done something like this. And when we do that, we're able to implement run here. And what a timer task is just something that we can use you can execute repeatedly. So let's see. So t.run, this will start it running. Now how much time it's gonna take will actually be determined by, I believe, the method itself somewhere. Let's have a quick look. I think it's called like the scheduler. Schedule timed task, Java. Okay. So this is for the timer.schedule method, where you specify a task, the delay, and a period. And we can see here this is what looks to be a public function, so we'll actually be using something like that. So I think I'm using the wrong class for this, because we need to be using what's called a timer, not a timer task. Now the timer, I think, has a task inside of it. That's what it is. I believe it looks like this, but we'll make sure. Schedule will include a timer task, as we're going to be specifying here. What is this? The delay and the period. So the delay is how long to wait before the first call, and the period is how often we call it. So we're going to say we're going for once every 60. I believe that's going to probably want to be an integer, right? I'd imagine. Did I miss something? I think I missed this. There we go. I swore this was a way to schedule it, but I could be wrong. Task. We'll call this step task, I guess. That's weird because I think I've done this before without having to implement the scheduler. But this should work as well. I don't see any problems with it not working this way. So all this says right here is to, because I believe this needs to be a long. Yeah, it needs to be a long. So we have to do math.floor on it when we do it. It's not applicable for an int and a double. There we go. So what this should do now is allow us to run a something on the timer, tick. And by outputting something like that, we're able to just make sure that it is indeed ticking every... this is going to be once every... or 60 times per second. So you can see here it's just spamming tick over and over and over again. And so we can see we have a ticking clock now. And all we're going to do is wrap our step function inside of there, and that's going to be our game logic that's going to constantly run. So whatever we put inside of step now is going to be part of our game logic, and so we have the game loop set up now. So now we have to decide what are we actually going to implement for our game loop. Well, the very first thing we have to do is see is to have like a block that we control, right? It's basically a new what can we call it? Like a tetramino? I don't know what you would call it, but it's defined as like a shape of 4 blocks that are taken up by the grid. So block here is specifically for a block in space. It's like a pixel almost. However, a tetramino, on the other hand, is defined by its shape of like 4 blocks, and it can be rotated. So this is probably like one of the more trickier aspects. Each rotation has a different set of blocks that it consumes around of itself, and you have to remember that it can rotate, so the rotation can only occur if all the blocks around it are free. And so we have to define what the block looks like for each type. And to do that, we're going to need a couple of different versions of the tetramino, ideally. One way to easily define this is to actually create a grid and then have each tetramino fit within that like grid space. So this is like I'm actually gonna name this like the shape class. That's more what we're going for. We're defining the shapes of our blocks here that we're gonna use. So for each block, we are going to use, let's say at max, a 4x4 array. That's gonna be the maximum size we need to fit any block into it. And we're gonna try to center the block as best as we can. So again, we're gonna create a set of, we can actually use our block class again to define this as well. So we're gonna use a set of 4x4 blocks, like so, to define our shape here. And when we do that, we can actually define it inside of here if we would like, because shape. Because when we do this, we're gonna define the shape ourselves. So So I want to make a constructor that just has active, but no color. So color can now default to something we'll actually call this, and just set color to black. That way we only have to specify active or inactive with one version of the constructor. So here I'm going to specify 4 elements, like so. And then I'm going to put one of these, and by putting by putting it like this, that specifies one array element, one array, I believe, if I'm not mistaken. Oh, I see. Let me define the actual array structure there, like this. And so that's one array element, but we need multiple array elements. So it's actually going to be new block array containing... Actually, I already have that specified up here. So each element inside the block array is going to have a block array containing 5 blocks. Or 4 blocks, excuse me. 1, 2, 3, 4. So this is going to be 4 by 4, right? And then we have to specify a shape. And it looks kind of... It looks a little janky. You could also interpret this using like text or something. That wouldn't be a bad way to do it. Maybe we should build a text parser for this to make it look less archaic, I guess. Because it might be a good idea to do something like that, where we just have a giant string, shape string, that we can specify. And the shape string itself can look something like this. You have like X's for any part of the shape that is inactive, and you can have O's or something for any part of the shape that is actually part of the shape. So something like this wouldn't be a bad idea, and it can be interpreted that way, as just 16 characters in a row. Makes it easier for us humans to at least make them, right? So I think this kind of gives us an idea of what we want to put for our constructor now. We want to specify a shape string. And when we specify the shape string, we're going to iterate through and assign this array based on this shape string we provided. So we'll say for int I is 0, I is less than shape string.length, I plus. We're going to iterate through all 16 characters, and for every 4 characters, we're going to start a new array element. So we're going to set up our shape array. Kind of like how we had up here, except we're now going to use this setup instead. This is going to be 4 by 4. And then here's where it gets a little tricky. We're going to do shape array. Which one we determine is based on the current shape, or excuse me, I, modulus 4. Every 4, we're going to the next, or excuse me, divide by 4. Every 4, we're going to go 1 over. So 0 divided by 4 is 0, 1 divided by 4 is 0, 2, 3, 3 divided by 4 is 0. Once it gets to 4 divided by 4, it'll start on the next row, which is the 5th element in the shape array. Here, we're actually going to use modulus, because for every 4, we're going back to 0. So 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, repeating over and over and over to store all these items. Finally, we're going to get the shape string character at that index. And that's going to be stored inside of here. And finally, we have to interpret this. It's going to be equal to... it's going to determine whether it's true or false. So we're going to specify new block. That's our constructor, right? And depending on whether or not this is equal to a O, determines if we're creating an active block or not. So that should be almost good. I need to turn these into single quotes. Single quotes specifies a character, which is what you get when you use character at. So this now defines our shape. So now we can define our shapes that we want. So we're gonna have to do that. Each shape has a, let's call it a frame. So the frame is basically contains 4 shapes, each one rotated a different direction. So a frame contains 4 of these shapes. And each shape is rotated in one of the 4 different positions. So we're going to be defining all of these frames with all these different shapes by specifying this shape string, but with different rotations of them. So when we initialize a frame, we're going to provide 4 different shape strings. Excuse me, we can just provide the shapes directly. So shape 1, shape 2, shape 3, and shape 4. And when we're done with that, we get a new array. This can actually be undefined for here because we're going to define it in the constructor. So we'll say new shape 4, specify S1, S2, S3, S4. Those are the different rotations, and we're going to make sure they are defined, I guess, in a certain order. So the first frame will always be like, we'll make sure the rotation is always clockwise. That's kind of what we're going for here. So the rotations will always be clockwise. Now that we have our frames and we have our shapes defined, we can actually set up all of our different shape setups for this game. So we got 6 different types of pieces, I think, or is it 7? I don't know. We'll figure it out, right? And maybe the frame wants to have a certain color too. It would be nice if we specify a color for the frame. So we'll just throw that in there, because that data will be useful when assembling the blocks. Alright, so we know we have the... I guess we'll call it the L piece or something, right? L piece. So when specifying these, we have to define a bunch of strings, which are shape strings, essentially. And we could kind of use this format here to create each one if we wanted to. Just to make it easier on ourselves to figure out what's going on. So for this, it's also going to be new shape. And you provide a string like so. Although I guess I can fix the indentation a little bit. So an L piece, it's probably something like this. Again, we want all the stuff to be like centered kind of around this axis, so when they get rotated, it feels kind of natural. So we said we're going to always rotate clockwise. So the rotation clockwise would look something like... Let me get out the insert. The insert would be very helpful here. And the caps lock. Caps lock would also be very helpful here. And we can keep on doing this. If I guess I need to set this up first. 1, 2, 3, 4. Okay. So this will provide you with 4 shapes, and then the color of the piece, I guess, will be, I don't know, orange. Orange is good. So that sets up one shape. And then we do the same thing for all the shapes here. I'm going to close this. This needs to be equal to color. Good. Close that, close that, close that. And we'll just work on the shapes for a quick minute here. So we're going to set up all the different shapes. 1, 2, 3, 4, 5, 6, 7. I don't actually know how many there are, but we'll figure it out, right? So we got, like, I guess what you would call the J piece, where instead we have something more along the lines of this. I didn't set up the other rotations, did I? So let's finish that, actually. Something like this. And then the last rotation. Probably look like this. Oh. That looks right to me. And the J piece is actually just the opposite. It's like inverted. So if I were to just copy and paste, we can invert these. I figure it would be faster to make the shapes by hand than to write an algorithm to detect the shapes, because we're only gonna have to deal with these once, so we don't need something to constantly rotate them all for us. Sometimes you can sacrifice like complexity in order to get speed. So knowing what you can program quickly and what you can't is a virtue. I guess we'll call this a purple. Do I even have purple? I do have purple. I forgot I have caps lock on. Alright, what else do we got? We got like these zigzag pieces, right? We got like, I guess I'll call it an S piece, because it's like an S. Kinda. Kinda starts like, kinda looks like this. Yep, something like that. And then it goes into one of these. And funny enough, when you rotate it a third and fourth time, it's actually the same shape. Like that, right? Wait, let me think about that real quick. Yeah, it is the same when you rotate like that. So yeah, that one can be the red one. Then we need a green one, which is basically the same thing, but just the opposite version of it. So we will copy that. What is that? That would be like the Z, I guess, because it's going the other way. If we're calling one S, the other one's Z, right? Is that right? That doesn't look right. Or maybe it is. Yeah, that's right. Wait a second. Hold on. Hold on. Let me think about this for a second. I have 5 blocks here. It's really just... Isn't it 4? Wait, hold on. These are only supposed to be 4 blocks, right? Not 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, yeah, I messed up a little here. You can see I went an extra like block over. So luckily I caught that because that's not good. I actually think I want to rotate it along this instead of this. Maybe. It's hard to say because like the middle is actually here. So really I guess I want to keep them top aligned if I can. You know what I mean? Like if we rotate it, I want to try to keep it like top aligned. Which means I would be moving these up by 1. Is that what I'm going with? I don't know. I'm trying to decide on what rules I want to use for this. And I think top aligned is a good idea. For consistency and for snapping ability. So that seems like a good idea. To have them always follow this consistent rule of being top aligned. That way when they rotate, they're always rotating along their top. At least that's the theory. When it's actually implemented, it might not feel quite right, so it might need changing afterward. We'll have to see, though. I'm just saying how I want to line this up, because you notice, like, I've got some closer to this corner. So it's always going to be biased, that's what I notice. It's always going to be biased to one direction or the other. You can't satisfy both with only a 4x4. So I guess it's whatever. So same deal here. We're going to go up to here, and I guess we will rotate it like this. 2, 3, 4. And that's gonna be the same shape 2 more times, like so. Let me make sure these are correct, because I actually did them manually, individually. Yeah, these are the same, and these are the same. So it looks correct so far. This one will be green. Alright. So we got LJ, SZ. We got the infamous T. And I think we got the square, or the O, I guess is what we would call it. And then finally we have, alright, so the T. I guess would look something like this. Rotated clockwise would look like this. So something like that then. So now we got an O piece. I think there's one more piece after this, so I might have got just the right amount of pieces, which is I guess it's like an I, right? The long piece? Anyways, the O is just a square. Easy. It doesn't rotate at all. All rotations result in the same shape. So just copy pasta that 4 times. And the color will be yellow, I guess. Something like that. What did I miss? Oh, I deleted the new shape parts, so let's put those back. Yes. And then finally the eyepiece has only 2 versions as well because, well, it starts off this, I guess. And it just ends up the opposite way. Oh. Okay. And you have the same thing 2 more times. And I guess we could call this like, what's the only color we have left? Actually, I don't know. I think we used them all, except for blue. Blue, yellow, orange, green, red, purple, orange. Okay, we used orange twice, so I think this one should be purple. So what else was purple? Anything? Blue, yellow, purple, green, red, purple. Okay, this can be, let me think. What color don't we have in here? Red? I don't think we... Oh, wait. We used red. Blue, purple. How about... I'm so confused right now. That's like all the... 1, 2, 3, 4, 5, 6. That's only 6 different colors, but I have 7 pieces, right? 1, 2, 3, 4, 5, 6, 7. Yeah. I have 7 different pieces. So I have to make up a new color. What are the colors normally? Let me see. Green, red, orange, yellow, purple, blue. I guess it's like an aqua color is what I'm missing. There is a blue, but there's also like this like aqua color. So I guess we'll call this one blue then. And this one can be aqua instead. Anyways, we have our frames set up. So the reason for making all these frames is now we gotta have a player piece, right? The piece the player is currently controlling. So that's just gonna be another frame, but it's gonna be copied from one of these frames here. So basically we're going to have the player frame reference one of these frames each time. So these are actually going to be final variables. These are variables that we're not going to change or modify. They are stuck the way they are forever. I feel like trying to think. Final's fine. So yeah, here we go. The player piece will be equal to one of these pieces, and now the piece that's chosen is determined at random from those. So we need to select from the pool of pieces. So we're going to make a frame array called piece pool. And we're just going to include all the pieces in there. So each of our pieces were named appropriately. So we'll just insert them here. Got the L piece, J piece, S piece, Z piece, T piece, O piece, I piece. all the pieces we can choose from. And now that they're in an array, it makes it very easy for us to select one particular piece at random. So to do randomness, we're going to be modifying the array element, where we will do an integer rounding on math times random multiplied by the length of piece pool. Now what this does is math.random returns a decimal number from 0 to 1. So it can be 0.6, 0.8, 0.2, and then if we multiply it by length, we'll get a scaled value between 0 and 1, scaled to the amount of pieces there are. So if there are 7 pieces, 0.5 would be 3.5, which would be 3. So we'll get piece number 3, which is the 4th piece, or the Z piece, and so on and so forth. So the player piece will be one of these pieces at random. In addition, the player piece needs to be located at a specific position. So not only do we have to store the frame, but we have to store where that piece is located on the grid at that moment. So we're going to need a coordinate. We can actually use like a... So I'm actually going to now create an official player object, because once you have to track more than one piece of data, in object-oriented programming languages, you generally want to put all the pieces of data associated with one thing in one class. That way all of those pieces of data are accessible from that class, and you don't have all these extra variables jumping around all over the place. So, player piece, going in there. So we're going to have a piece. And we're also going to have a coordinate, which we're going to define as a point right now. The point is going to determine where in our grid our player piece is currently centered on. And it's important to say that it's centered on it, because what we're going to have to do is every single block is going to be checked from that center point to see if it collides with any other piece, which we're going to get to a little bit later. So this is the current position, I guess, as we like to call it. So point is just a Java class. I believe it takes in integer precision, so that's exactly what we want. And what position do we want to start at? Well, we haven't really defined what our grid system is going to look like, but ideally we want to define it the same way that this array is set up, so it's easy to navigate. So if we increase along the y-axis, it's going to influence this value. And if we're increasing along the x-axis, it's going to influence this value here. So, where do we want to start? Well, we want to start at the top of the grid. So we want to position our piece at location, let's see. The center will be a grid width divided by 2, which is 5, and a grid height of 20. We want it at the max possible position. So when the player object is first initialized, the piece will be set to a random piece. So we will do a piece pool here. We're actually going to make this a static variable, accessible. Wait. Why is this, Oh, we have to initialize it. You can't define a variable inside of a class, so define outside. Only finals permitted. Oh, we're not in the class. There we go. Okay, I'm like, what? Anyways, piece pool defined here. And by making it public static, it's accessible from other classes. So back in here we go. And we're going to define our piece to be a random piece. So we're actually going to be moving this over here. And we can refactor this if we really wanted to. We're going to make sure we reference game.piecepool, because that's static now, so we can. We're just going to say, it's called select random tetramino. That works. Select random tetramino to be assigned to a piece. And finally, the position. The position we already established will be set equal to, we have to specify a new point located at 5, 20. That is where we're going to start at. So, with all that set up, now we have to create our player class. So, player P. I like to use P because it's short and simple, and we're going to be referencing it a lot. I'm actually going to define it up here because it should be available for many things. So here when we define our new player, We don't have to actually specify any arguments, so it'll all be specified for us. But now we're ready to actually do stuff. Additionally, I think Tetris usually stores like a next piece or something, so it knows in advance what the next piece is going to be. So how about we make a next piece frame right now, and we initialize that as well to be some random piece. Select random tetramino. And now we can start defining our functions. Like for example, the first thing we have to do is create some falling logic. The block has to fall down on each step. At least, I guess we have to specify like a game speed, right? You don't just fall down every single step. That would be way too fast. Like, ideally, if a piece falls 60 times in a second, you're barely gonna get a piece. You're barely gonna be able to play the game. You won't even see what's going on. So I guess we need to add some delay, or like a level system or something that determines how long the delay between each piece is falling. So we need to have like a timer of some sort. How long before we advance the block? So we purposely slow down the game to add a like level system to the game. So I guess we can define this. Let's define it as levels as like the delay in frames. I think that's a good way to do it. So we'll have an integer array called level delay. And I guess we want to establish this out here because it's a game property. So level delay, we will initialize as a new integer array. And let's say we have, oh, I don't know, Tetris has maybe like 20 levels or something. So at level 1, let's say a piece only moves every half a second. So that's 30 frames of delay. And then level 2, it can be like, I don't know, 25. And then like 20, 18, 16, 14, something like that, right? How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, perfect. That's 10 values. So I guess as we get closer and closer to level 20, 1, 2, that's 9 values. Maybe we decreased it too quick. Let's try something a little more sane. I think we decreased it too quickly. 14, 12, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And that should be 20 values. Let me double check. It might tell me if I just mouse over this. Nope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We got 20 values to represent the level delay. Now we need an actual value to represent what level we're on. So we're going to include what level we're on. We're going to start at level 0, which is really level 1, but we're going to say it's 0 so we can reference the correct level delay value. And then we're going to have to store a value that determines how much time is passed until the next tick. So tick delay will be 0. Actually, it will be 60, and then it'll start ticking down based on step. So that's gonna be our first logic. Is our first actual logic for step is we're gonna say tick delay goes down by 1 with each step, and then if tick delay is less than or equal to 0, then that means it's time to do an actual tick. So this will be like a move block method, which we're going to define a little later. And then after we do that, we're going to say tick delay will be equal to whatever the level's delay is. Kind of like that. So that way we're resetting tick delay after we're done moving the block to indicate the next tick. So now we have a constant iteration where we're counting down, then we're doing the move block function. Now the move block function is actually going to be the brunt of what the Tetris game is required to do. So basically every time we move the block, we need to check all squares that the Tetrimino will occupy, right? If any squares come in contact with an active square, this block will snap, and all those squares become active on the grid. Then, update the current piece for the player to the next piece, randomize the next piece, and set the player position back to 5,20. Additionally, we have to determine which rotation of the shape we're currently on. So we're going to be storing that in a value. We'll call this, we'll just have an integer called rotation, and it'll be set to 0. It can be a value from 0 to 3, representing all the rotations, the shape rotations that are that are available for each piece. So, with that logic set up, let's first deal with just a 0 rotation. So, to check all the squares, what we're going to do is first grab the shape that we currently have for our Tetrimino. So, tet shape is what I'm going to call it. Is going to be equal to whatever player.piece, P is what I called it. P.piece is dot shape rotation. Because we have rotation stored, we can grab that shape. Then, we have to grab all the squares that have O's in them. So we're going to make a quick point array called checkpoints. And they'll be equal to all the points that match up to that. So new point, we know it's going to be an array of size 4 because all blocks are only 4 large. So at this point we need to import point, and we need to add an equal sign because we forgot it. And now we are going to actually check all those points. So we have to iterate through our shape and actually identify all the O's and where they are located within the shape. That part's important because we have to then offset it by a certain amount. So as we go through the shape, like this is starting at 0, 0 offset, right? So this is the first shape will be at a 1, 0 offset. Or wait, let me think. It's gonna be centered around the player, I think. So really this, the middle here, like, is going to be 0, and then this is -1, -2, this +1, +2. And then down here, it's going to be -2, but 1 below the player's Y, which is actually -1. So it's a coordinate system that goes from the center being the middle axis, and then the top being the x-axis. So y-axis is through the middle, x-axis is through the top. So we're going to iterate through our entire shape. I is less than tet shape dot shape string I++, right? This should be length, the length of that string. Is this an array? It should be an array, right? No, this is a string. Okay. So it is length, the function. Arrays use the dot length variable, but strings use the dot length method. So a little bit different there. If tet shape character at I is equal to an O, then we know that's going to be a position we have to check. And we have to actually do this for character comparisons. And it's shape string, whoops, shape string I dot character at, wait, dot character, there we go, shape string dot character at I is equal to an O, then we know we're going to be using that position to determine the next point to check. So what point is that going to be? Well, we have to actually add it in. So we have to store how many points we've inserted already. Points inserted will be equal to 0. Then every time we insert a shape, we increase it by 1. And if we happen to get them all, we can then exit. But we know there's going to be 4 O's regardless, so that would kind of be a pointless check. But what we're trying to do is make sure that we're inserting into the correct position in the checkpoints array. So we're going to be doing that. Checkpoints, points inserted, then increments it afterward. So it's going to be 0, and then it's going to auto-increment. It's a very nifty syntax to use, especially if you're going to be doing plus plus. So we're going to make it equal to a new point. And what position will it be at? Well, the position is determined by the actual iteration in the loop here. So again, we're going to kind of be using the same logic we used when establishing the shapes here. So yeah, this kind of ended up being a pointless endeavor because we're just going to end up using our own version of this anyway. But the X position is actually going to be, while it is I divide by 4, it's also going to be I divide by 4 minus 2. Because we're talking about like a relative offset in relation to the player here. So we're always going to subtract 2 from the grid starting point for the X position. And then the Y position will just be I modulus 4. So if we're on the top row, it's just going to be... Wait, no, I think I have this backwards this time. So the X is going to be I modulus 4 minus 2. And this one's I divide by 4. The reason why this is because on here, the X position, the leftmost position is going to be 0. Then as you go across, it's going to be 1, 2, 3. And then when you go to the 4, well, now you're back at the 0 position along the X-axis, but now you're at the 1 position on the Y-axis. So these two need to be flipped. And thus we have our checked points. So once our checked points have been established, we are actually going to compare it to the places on the grid in relation to the player's position. So now we're going to iterate through our checkpoints, which we can actually do now using an iterative loop here. And we want to be careful because we don't want to use the local variable p, since we need that to access our player object. Otherwise, we're going to have to specify game.play.p, which is going to be more annoying than just specifying p. And so we now have to check if that position on the grid is occupied. So if grid, or excuse me, what did we call it? Did we store it? I don't think we did. We didn't store it up here. So we need to do that real quick. Boom. And we will make it static like the rest. It is available to the entire game. So now we can specify here game grid. And we're going to be checking a position on the grid. So what position? The position is determined by the offset from these 2 points. So one nice thing about the point class is that you can actually add, I believe, 2 points together. Translate. Translates the point by dx along the x-axis and dy along the y-axis, so that now represents a different point. But I think this modifies it in place, so we do have to be careful to modify the point that we're not going to be using anymore. So we will do point dot translate, and the amount we translate it by is by our player position. So we do p.pos .x, p.pos.y. So we specify 2 points, 2 positions here to translate our point by in order to determine where to look on the game grid. Because this position plus the player's position will equal the position on the grid that we have to check for. So for example, if the player's block is located at the top, 5, 20, and we are using, say, one of the simpler pieces, like a rotated, or O block is pretty simple, then this position will actually be -1 and 1. So it will actually look at position 4, 21, which will be the next, or not 21, 19, to determine which position to be at next. Speaking of which, I need to add a negative sign here, because as we go further down, we're going negative, not positive. So that's something to keep in mind as well. And on top of all this, this only determines what position that block is at. So for example, again, this block at this coordinate would have this little dot located at position 4, 19. And that's where that block is located. But guess what? It needs to fall down 1, right? So if the block has to fall down 1, then we need to check not 419, but 418. So we're actually looking at point.x, point.y minus 1. We're looking 1 block ahead, and then we determine if it's active or not. So if this is active, that is when we have to say, okay, this is occupied, so we have to do something with that. Boolean is occupied is false. The moment we've determined that it is occupied, we're going to break out of the loop, and we have our next set of logic. So if the position we're going to for any of these points is occupied, it means we can't move the shape down because it's going to collide with another shape already on the grid. So we just take all the points that are currently here, and we set them up, or excuse me, not here, here, and we set them up to become permanent points on the grid. So we're just going to set them all active. So we're going to copy this loop again for every single point in our list of checked points. We're now going to set active equal to true, because now it is active. And now, since we have snapped the block completely, we need to do our logic where our piece is now equal to next piece. Excuse me, p.piece is p.next piece, and then we select a random tetramino for the next piece. So we will call this, we'll make this one public, shuffle next piece, which will do next piece will be equal to select random tetramino. Yes, like so. Seems good. Oh, this needs to return nothing. We just need to say shuffle next piece. Like so. Alright. And actually, we can include this logic in here too. I mean, this makes sense to me, right? So piece to next piece then is equal to select random tetramino at random. The only bug I could think of that might come from this is that this is going to be equal to a pointer to this, which means this object might be equal to whatever this is on the next step. So we have to be a little careful. I would say we should include a clone function, but in order to clone the function, we're going to have to actually implement an override to clone. But I think we have to do that to make sure we're not referencing something bad. Because each of these frames represents a piece, and then that piece is going to be referenced by this next pointer, which is going to be chosen at random. However, this, I think, gets a new piece each time. In any case, we do need like a cloning function, so I do have one of those, luckily. I use it occasionally. It's not a big deal, but I put them in my reflect utils. Is clonable. That's not what we want. Java utils maybe. Here we go. Clone. And this is where we need is clonable as well. So these two utils, I'm gonna bring them over. I actually like to bring over sig.utils in general, no matter what kind of project I'm working on, because sig.utils is full of fascinating things that we've built over time. Unfortunately, this is way too large, so I need to like actually copy this into here. Alright, so sig.utils gets added to here. We're only concerned with Java utils, so we're gonna be grabbing that. Inside of Java utils is a function we can use to override a class's clone to specify what we need to actually include for a clone. So you can see here, it actually tries to clone all of this, which it kind of just does it on its own. We don't really have to do anything specific here, but it's nice. And the reason why we have to clone again is because this is going to be referencing a pointer to this object. Oh, speaking of which, we need to override the frames clone, actually, because that's what we're trying to clone. Trying to clone this, so if we're going to clone that, we need to reference that .clone. So by calling this, we're now going to need to... what? Hold on, I'm referencing the wrong... It's returning a Java utils. It needs to return the class. So let me change that. Whoopsies. Needs to return a frame. Okay. This needs to be a frame. This needs to be a frame, which needs to be specified by, again, all these shapes are stored in the shape array. Like so. And a color. And that creates a clonable thing that we're gonna need. So I don't need to clone a player. That's not necessary. Alright, back over here. We're gonna shuffle the next piece. And then finally, we're gonna actually set the player position back to where it's supposed to be. So shuffle next piece will do that for us. Pause equals new point 520. Now what happens if we're not occupied? Well, we just move the player position down by 1. Pause, not pause, P, pause, translate. 0, -1. We just moved down. So that's all we're gonna do for now. This is gonna create a falling block simulation, at least ideally, with random tetraminos, hopefully. In order to prove that this works, we're gonna actually have to output this somehow or in some way. Again, we don't have a graphical user interface yet, and we're probably not gonna have it until tomorrow-ish, but that's fine. We'll at least get this part finished up for today. So back in the step, we're gonna constantly output what our field looks like. I think it's a good way to just so what we're going to do is output constantly to this to here. So we're just gonna write test console. The reason why I'm gonna do this is I want to make sure the flush works correctly. So we're gonna run this now. So you can see there was a null pointer exception move block, which is so was P defined? It was not. So we need to define a new player here. That would be a good idea. And select random tetramino is also exception initialization error. So we can't initialize a player here because not all the variables have been initialized. So, oh, I see. We initialize player down here actually. So why then do we get a null pointer exception is the question. Now, does position get set? Position gets set when player gets called. So, new player set up here. and then we do move block inside of step. So therefore, by the point it gets to here, maybe we have points that are null? Let's see. Well, X and Y should definitely be set up. Let's output some things and see what happens. Output P. Oops. I wanted this to be like a string. So we can see here it's a 520 and then a null pointer right after that. And it says it's at line 221, so something here is null. I guess we'll find out. So point is indeed a null. So I don't think this iteration version works for arrays. That's what I'm getting at here. So we'll just iterate through it like we normally do for arrays. I is less than checkpoints.length plus plus. Then we can set point equal to checkpoints I. That way we essentially accomplish the same thing. It's still pointing at null pointer, so I think there's something else going on here. We'll have to check this out now, because this clearly is not working the way it should, from what I can tell. So we're gonna see if shapestring character at is equal to O by just outputting. Let's just first output what the shape is. Make sure that part's working. So we can see there's a bunch of X's here. That's not good, because they're supposed to be X's and O's. So we're supposed to get a piece pool from here. This piece pool contains one of these frames, and then each frame contains 4 shapes, correct? Yes. Each frame contains 4 shapes, which is an array. Then we use the rotation variable to determine which one of those shapes we're using. And none of these have an XXX version, as far as I can tell. Across of its entirety, as far as I can tell, right? Let me make sure, because that would be kind of whack if I did have one. Okay, so I don't see one there, so we're gonna look at new shape now. We can see shape string is like this, but we're gonna be using the argument provided by shape string there. So it shouldn't be using this, that's for sure. Also, I think we totally forgot about this array here, because we do want to store it inside of there when we are done calculating it. Like so. Shape equals shape array. I don't think we have to specify anything here because we're just going to specify it down here. But, you can see now shape string cannot be resolved because that's not what we wanted to store. Now, we actually get something we want. So funny enough, now we don't iterate through this, we iterate through the X and Y positions inside that array. So we're going to be changing our structure a little bit. We're going to call this the Y. Y is less than tet shape length. And then inside, we're going to iterate through all the X's. Because each Y that is located in here has an X. Actually, all the X's are stored in here, aren't they? I mean, it doesn't matter which way you iterate through them. It's just I'm trying to make sure I understand which direction we are going through them. So we're just going to select from array 0 each one. So, with that in mind, we kind of use a similar idea we used up here. But we're going to say, okay, so tetShape.shape x, y dot active. Then we know that block is going to be one of the checkpoints. So then we set checkpoints. Points inserted. Like I said, we're kind of following the same layout we did earlier, but here instead we specify x minus 2, I believe, because we are taking whatever x we get, just subtracting 2 from that. Then we got y here, but we're going to take the negative y, because as we go further in the array, we're actually going down in the grid. So that's actually what we're doing there. Alright, so I don't think we should have any more null pointers, at least. So we can see here test console is just spamming the heck out of this. So at this point, we need to display, like, something, right? So this is what, this right here is what we're going to call the clear screen. Clear screen. And then afterwards we're going to do this. Test clear. This makes sure that each time we run it, we basically have like a clean slate to start with. So if we look at this now, it's got these, but they're separated quite a bit more. And this gives us like a clean slate to work with. So now we're going to output for each row of the grid. Y is 0, y is less than 20, y plus plus. And we actually want to start from the top and work our way down. So greater than or equal to 0, because we have to go down, not up. X is 0. Then we increment x. As we go along the grid, going across the screen, we're going to print out each one of these. So we're going to print one character. We're either going to print O or X, depending on whether that part of the grid is active or not. So game grid dot grid x, y is equal to, or dot active. And if it's active, we're going to display an O. If it's not, we're going to display an X. Or we can display a dash or something, just something small, to indicate there's nothing there, right? And then for each Y position, we're gonna add a new line. Just like that. And so we can see here, array index out of bounds exception, starting at 20 is not the best idea, so we're actually gonna start at 19. So you see here we just got blank grid apparently. So nothing has happened yet. So one thing to note is that the dot active is only when these blocks are visible. So another thing we can do is then draw the actual player thing on top of it. So this is the logic to draw each item in the game grid, but then we also have to draw something to indicate where the blocks for the player instance are located at. So we can do that as well. It's a little more annoying, but this right here determines what points, or excuse me, this right here determines where in the game grid the player's block is. So this is like essentially the data we need. So you can see we have to go through this loop, and then we have to go through this each time to figure out all the game's blocks, basically. And it's kind of annoying, right? So we're gonna end up making something to help us interpret this without having to go through all this part. So this is where a utility function can come in handy. And I think this is gonna be the last thing we implement today. So we're gonna implement a small utility function for checking where a block is in the grid, which is gonna just follow this. So that's gonna be done inside the player object. Get player blocks in grid. So it's gonna return a set of points, just like this did, to determine where it is in the grid. And it's gonna be in grid coordinates. So, what it takes in, it doesn't take in anything because we already have all the known data points. We just need to figure out where we are in relation. So we're actually gonna be moving all this into here. We're basically refactoring this code right now. So we need our current shape. So piece.shape is what we're gonna be using here instead of tet shape. Hold on. This is a shape array, right? Yeah, that's not gonna, this doesn't make sense to me because this is a shape array. So if this is a shape array, then .length should exist for this. Could be wrong, but I believe that's how this goes. A frame has a shape array. The shape array has shapes inside of it. Oh, we have to get the shape's rotation. That's right, I forgot about that. That's why we have this here. Okay, that makes more sense. I'm like, I think we're forgetting a step here. Boom. So to get our current rotation, that's actually stored in the game object. If I could type, that would be nice. So here we now have to store our points again, so we're gonna do that. Basically, like I said, we're essentially refactoring this all into here instead, because that is actually very helpful for us. So we got all these pieces in there, but we're not quite done. Well, actually, we are done because we have successfully refactored all of that. So this is just gonna return checkpoints now. But we still want to get them related to this. We want to translate all of them so that we don't have to do it later ourselves. So, with all these points, we're now gonna do a translation on them. So we can do that, .translate, and we'll just say pause X, pause Y. And that gives us a translated point already. And we can't operate it directly because we need to actually store it first. So I kind of made this a little more complicated than I wanted to, so we'll just back this up a little bit. Point. Yes, great name. Call the point. Anyways, that's gonna be stored inside of there, and then we'll take point.translate, and we'll make sure we adjust it accordingly. Like that. So then, now we return checkpoints. Boom. And we have our function there. So all of that we had before now gets stored in player blocks in grid. Now the only difference between using this and what we had before is that we're already returning the translated version. So player blocks, or we called it checkpoints. So we don't have to translate them anymore. We can just iterate through them directly. And this needs to be from player, like so. So that takes care of that logic. And so we have these available to us now. And we can use it up here now without all this other mess. So we go up here, we say, okay, get our player blocks in the grid. If any of them match up, we're also gonna draw an active block at that position. In fact, we can draw it with a different letter if we really wanted to. So we're going to check for all points inside of checkpoints. We'll see if any of them match our current position in the grid. If so, then boom, plot it down. If point.x is equal to, in this case, I think x, we just literally check for x, and point.y is equal to y. Yeah, then we plot it down. Otherwise, we don't plot anything because we might have to output something else. So we're actually going to here. Boolean plotted is false. So plotted becomes true if we did plot it. So we don't have to plot anything here if we already have a player block plotted out. I mean, theoretically, you could still run this because player blocks should not collide with anything on the grid already. But if they do, then we have that logic at least there, just in case. But really, it's unnecessary. Like, I can... Well, actually, it is necessary, because otherwise we would just draw extra dashes when we don't need to draw extra dashes. But we need to turn this into an if statement, because we don't have an else case. We can't just draw nothing. We have to draw a character. So, instead of this logic, though, we need to say Wait. Why was that? That didn't need an if statement, actually. Yeah, we just literally output the letter P. Otherwise, we keep going with this. Oh, and then we need a break, because we don't need to stay in here. Alright. So you can see, here's our falling tetramino. And so, you can see that that part works. Now, we don't have any collision with the bottom, which is something I forgot about. So, we have collision with other blocks, but we don't have collision with the bottom of the grid. We can't keep going past the grid, because that will be an out of bounds exception, as you can see. There's no -1 in the array, so all we have to do is, we have to check if we've reached the bottom of the grid, first of all. So, if point.y minus 1 is less than 0, then is occupied. We'll just say it's true, and we'll break. So, because you can see these two use the same statements, we can actually combine these here to create an OR. So if either of those conditions are true, then we break out. Simple enough. So let's try that one more time. You can see is again the falling block, and then once it reaches the bottom, this time it should actually nope, it still tried to move. So what is going on there? We can see here it tries to set up .active. So you can see here it tries to set up y minus 1 is less than. So our logic is kind of wrong here. We need to check 1 before. So far, y minus 1 is equal to 0. So we have to say less than or equal to 0. Then yeah, we're done. We have to drop right there. Simple enough. So you can see there, it just turned into a part of the actual grid, and then the next block spawned, and it's probably gonna stop where it should. Oh, it collapsed 1 further down. So that's something I was worried about. It might actually drop down 1 extra position. So we need to actually make sure that doesn't happen. Because if this statement is true, then we don't drop any further. What position we're at is where we're stuck at. So that's where I messed up. Whatever position we're at, that's where we're stuck at. Now here it drops 1. So now we can go back to our previous condition where if we go negative, then we know we can't drop any further. So we just had some bad logic there, mostly because of this right there. So now we should be good. At least we hope, right? I mean, worst case scenario just still doesn't work, but I think now it should snap to wherever the blocks can land. So now, yeah, now we have stacking blocks. Now eventually it's gonna get to the top, and then the blocks are just gonna keep snapping forever. But as you can see, we do have a successful working drop part. So the next thing to do, which we'll work on tomorrow, is rotating piece functionality, obviously, and then clearing lines, and then finally the graphical user interface. I feel like this will be done in like 2 or 3 days. But this was a nice hour session. It went a little bit over, but it's okay if it goes a little bit over as long as we're learning and having fun while doing so. So, hope you all enjoyed. We'll continue this tomorrow. For those of you that tuned in, thanks for watching. It eventually dies because it's like, oh god, what do I do?